So compiled a document about frequently asked questions and errata on Piazza. And if you are just starting on assignment 3, please definitely check out that document. And it is pinned at the top item in the Piazza. So actually, to start this lecture, I would like to go through several important frequently asked questions about assignment 3. And these frequently asked questions are actually also mentioned in the document that are pinned in the Piazza. So first of all, what data set should we use? Only the IMDb data set. So the assignment 3 writes only the IMDb data set. But if you take a look at the README, it also mentions some other data set, which is the SST5. And in this assignment 3, it's not necessary to do anything about the SST data set. We could just run the training and the validation on the IMDb data set, and that would be nice. And that would be sufficient. So for the IMDb data set, the test set does not contain labels. So if you try to compute the test set accuracy, you will see some very random numbers. This is because both of the positive and negative samples in the test set are labeled 0, which means the IMDb test set does not contain labels. So in writing the report, only report the training and validation set accuracy is sufficient. So only the training and validation set accuracies. So question 4.1, how to load the checkpoint. This is also a frequently asked question on Piazza. 4.1 requires loading the checkpoint. And in the question 3, if you use the GPU tensor, if you use the GPU devices to train the model, which we actually recommend because this is faster, around 10 times faster than training on CPUs, then the checkpoint have the GPU tensors. So the tensors are marked of the device GPU. And this means that if you're loading this checkpoint, then you also need to run on the GPU device. Otherwise, the model also, otherwise, if you instantiate this model on CPU, then this model accepts the CPU tensors. And it's going to report some device mismatch if you directly load the GPU tensors. So here are some methods to get around this problem. So the first of them is to just launch a script, Python script on GPU using Slurm. And Slurm can be run by either srun or sbatch. And then you can paste the result into the notebook. So this is probably the most obvious solution. And the second solution is to run a Jupyter server on the CS lab using GPU. So you can launch a script on GPU that sets up the Jupyter server. So essentially that is srun Jupyter lab, something like that. And that script or that command actually launches the Jupyter server, which listens a port on the CS server. And this port is usually port 8888. And you can check the log message to decide to find which port it occupies. And then you can forward that port to your local machine. And then you can visit that port through your local machine and visit the Jupyter server on your favorite browser. So, and the third option is for those who want to do some experiment. So you can modify the classifier.py script, and you can. There is a function called save checkpoint, and in that save checkpoint function, you can shift that model from GPU to CPU, and then save the checkpoint, and then shift the model back from CPU to GPU. In that case, the checkpoint would be based on CPU tensors, and then you can directly get the model checkpoint on CPU machines. And there are also a lot of other options, and there's no restrictions of which option you use to load the checkpoint. And also, there's no restriction of whether you use CPU or GPU to acquire this checkpoint and train the result. So actually, although we highly recommend using GPUs, because that saves you a lot of time, some students also decide to use CPUs to train the models. Using CPU takes around 20 minutes to run one epoch, and using GPU takes around 2 minutes to run one epoch. If you decide to use CPU, that's also fine as well. So essentially the answer is whichever works is accepted. So any question about 4.1? Okay. And then 4.2, yes or no, or positive, negative. So on the handout, there is a typo. The handout asked the students to prompt the model with this movie review is yes, or this movie review is no. So these types of prompts do not make sense semantically. And the prompt should be this movie review is positive, or this movie review is negative. And these types of prompt will make a lot more sense to the models. So if you change the prompt from a yes or no to positive or negative, then you are going to see some model outputs that make a lot more sense. But because the handout is already yes or no, you can also query yes or no to the model and report whatever the model outputs. Actually, we encourage you to try multiple prompt formats and see if the model outputs make sense. And you can include them in the discussions. So are there any questions about the assignment 3, question 4.2, or assignment 3 in general? Okay, if there's no other questions, let's start the information retrieval lecture. So information retrieval is essentially it's a process to retrieve the corresponding document from a knowledge base. So an example is that if someone asks which woman has won more than one Nobel Prize, and an information retrieval procedure is going to return the answer, Marie Curie. So there are some key components in building an information retrieval system. A query, the process to search, and also the document that is returned by this search process, and also the knowledge base that you search from. Actually, information retrieval systems are very popular nowadays. Almost all of us use at least one of the information retrieval system on a daily basis. So Google search engine is an information retrieval system, and the Amazon search box is also an IR system. In the past few months, the market share of Google search engine is decreasing by a little bit, and this was partially because some people are using the search engine provided by Bing. So Microsoft Bing actually couples the search engines with its GPT-4 model. So if you search something on the Microsoft Bing, you are automatically connected to GPT-4, and this model is going to be able to sort of do some chat with you and analyze the problem that you are searching. So I personally find it very interesting. And that is probably one of the reasons why Google has an internal red alarm in response to the Bing's GPT-4 search engine. And I believe Google is going to incorporate their BARD model into their search engine in the short future as well. So in the future, the information retrieval system might look more like chatbots, but in the essence, they are still information retrieval systems. So we give them a query, it searches in a knowledge base, and it finds the item that matches our query the most. And usually, these types of search engines do not only return one result, they return a page of results. So this is a generalization of the model that we are discussing in this lecture. So in this lecture, we're discussing a simplified information retrieval system where the search engine only finds the item that matches our query the most. But actually, this type of modern search engines can return multiple results. It can return like the 10 results that match our query the most. So So I'll briefly mention the algorithms in a few slides. So to build an information retrieval system, we need to address the 3 key problems. So how to represent the query, how to store a knowledge base, and how to search efficiently and accurately. So to represent the query is usually just considered one of the document, which is just a string based on text. And recently, there are some consideration of the multimodal document. So, for example, in Google, you are able to search for more than the text-based document. You can also search for images or videos, and these are allowed by the multimodal embeddings, but for the sake of describing the foundations of the information retrieval, let's consider only text-based documents. So query is text, and document is also text. So a knowledge base is usually a collection of documents, and these documents could contain text of different languages. They could contain documents of variable lengths. And some of the documents are relevant to this query, and a lot more other documents are not relevant to this query. So we need to search efficiently and accurately for those documents that are relevant. So by accurately, I mean we need to search for those, we need to return those documents that are relevant. And we need to be able to do that very fast. So these problems are closely related, and we will look at some popular approaches to address the information retrieval key problems. A simplified scenario is supported by the structured query language. So if you have taken the CSC401 you are familiar with the structured query language. It is able to, with SQL, you are able to represent the query in the SQL queries, and you can store some knowledge base as some tabular entries. And also with SQL query, you can specify the schemas, which are basically what columns does each table have. And you can put some queries, you can put some documents into that table and construct the knowledge base using SQL. And also SQL engines allows you to search efficiently and accurately. So there are some engines like MySQL or NoSQL that allows you to compile and execute those queries. So the details of SQL is not part of CSC401. So I'm including the simplified scenario as a simplified example of how the information retrieval system works. Also, the SQL knowledge, the SQL database involves a lot more than information retrieval. So with the SQL database, multiple people can query at the same time, and multiple people can also write and modify the items in the database if allowed by the synchronization conditions. But for the information retrieval, we do not care about modifying or updating the items in the knowledge base. We only care about finding the corresponding items. The goal of the information retrieval is to just find those relevant documents and return those documents to the users that send this query. So scenario 2 is maximum similarity search. This might sound familiar to you if you come to the ASR lecture. So in one of the simplified systems in ASR, we described a maximum similarity search. So in that system, we assume that all of the sentences only contain one word, and every single word only contains one possible sound. So we can, in that case, we can just store all of the word and as well as the corresponding sound into a massive dictionary, and we can, whenever we hear some sound, we can convert that sound into vector and do a maximum similarity search and find the item in that massive dictionary that is maximally similar to the sound we hear. And the sound we hear is actually the query. So in IR system, the maximum similarity search works similarly, except that both the query and the items in the knowledge base are vectorized documents. So to represent the query is just another text-based document. And all of those documents are vectorized and stored in the knowledge base. And to search accurately, we can compute the similarity score between the query and each of the documents. And we can return the document with the highest similarity score with the query. So the similarity score can be sort of visualized here. So in a two-dimensional space, each vector of the document can be plotted here. For example, D1, D2, D3, and if we have a query, which is also vectorized in two-dimensional vectors, it's Q here, and we can see that the document that is closest to the query is D2. So the similarity here is represented by the angles between the two vectors. So this can be computed by the cosine similarity. The larger the similarity is, the closer the two vectors are. And this relation generalizes to the higher dimensional vectors. So you can compute the similarity between the different vectors in high dimensional spaces. And then you are able to see the similarities between the vectors. So in addition to the cosine distance or cosine similarity, you can also compute some other types of similarities, like those similarities that are based on L1 or L2 distances. So are there any questions about the vector similarity and maximum similarity search in general? No? Okay. Then let's start describing the procedure of one popular vectorization method, which is TF-IDF. TF-IDF consists of two parts. So this is an effective vectorization method that computes a vector based on the occurrences of the words inside. And the two parts of this vectorization include TF and IDF. And TF means term frequency. IDF means inverse document frequency. You can see that the term frequency is the number of occurrences of each particular word in the particular document. So if we use I to index the word and J to index the document, then the term frequency of word I and document J is the number of occurrences of word I in document J. So this is the occurrence, although it's called frequency. So this is a weird convention in the information retrieval literature. So people refer to the occurrences by the term frequency. And the document frequency describes how many documents in which this particular word appears. So if a word is very popular, it occurs in a lot of documents, this is actually a negative indication of relevance, because this word might be those kind of functional words like of, the, a, in. This kind of words occur in a lot of documents, but they do not actually carry a lot of meanings. We would like to find those words that carry the most meaning, which means they only occur in a few documents. And we would like to use the frequencies of those kind of words to represent the characters of this document. And of course, there are the collection frequency, CF, which just describes the total occurrences of that particular word in the collection. So let's look at term frequency closer. So a higher value of term frequency suggests that this particular word, W of J, occurs a lot in document D of J. So if the word occurs very frequently in the document, then that means that this word might be a good indicator of the contents of this particular document. So if this word is a meaningful word, it's not a functional word, then we will definitely expect to see this word occurring very frequently in this particular document. So we would like to see a larger value for a better indication of the similarity between this document and the query. So TF term frequency is larger is better. And empirically, we also dampen the term frequency to make the comparisons look less extreme. So by taking the logarithm, we're flattening out the probability distribution. No, we're actually flattening out the numbers of the term frequencies. So, and after that, we're adding 1 to the logarithm values, just to make the values more positive. So let's take a look at document frequency now. Document frequency is the number of documents in which this particular word appears. So we need to tell apart between those meaningful words and the functional words. The functional words may be distributed quite evenly over all the documents. And although they have a lot of high term frequencies, the functional words are actually not that relevant to our query. So ideally, we want to dampen out or dump out the contributions of those kind of functional words. And this is made possible by the document frequency. So let me illustrate what I mean by this example. We are comparing two words, kernel and try. The word kernel has around 10,000 collection frequency, but it occurs in around 4,000 documents. But the word try, although has a similar number of collection frequency, it occurs in more than 8,000 documents. So you can see that the word kernel occurs in a more specific context. It occurs in a lot fewer documents, which means that the word kernel is more meaningful than the word try. And here, the word try is more functional than the word kernel. So document frequency can be used to indicate this kind of differences between the words. So practically, we compute the inverse document frequency because we also want a score that is higher the better. So the term frequency is higher the better, but document frequency is lower the better. So the way to convert the document frequency into something that is higher the better is to take the inverse. And also following a similar approach, we take the logarithm. So the inverse here is D divided by the document frequency. And D is the total number of documents. So I also have a motivation based on information theory about why take the logarithm in the document frequency. And I will talk about that in the next slide. So for now, let's take some look at some extreme scenarios of the inverse document frequency. So imagine that if a word only occurs in one document, then its DF equals 1. So the inverse document frequency value is essentially log of D divided by 1 equaling log of D. This is the maximum value of the inverse document frequency. And what is the minimum value? The minimum value is acquired by getting those words that occur in all documents. So the document frequency can't go beyond D. So D divided by document frequency can go no smaller than 1. So at the minimum value, this word occurs in all documents. So IDF equals logarithm of D divided by D, which is logarithm of 1, which equals 0. So the inverse document frequency has the maximum value logarithm of d and minimum value of 0. So here are some additional motivation based on information theory, and this part is not in the exam. So this is just to help understanding of why we take the logarithm in both the document frequency and the term frequency. So we can, as can be remembered from the information theory lecture, when we observe some less likely event, then we get more information. So the amount of information that we acquire by observing some event is the logarithm of 1 over p. And in this context, the inverse document frequency is exactly the information we observe, the information we acquire by observing this document contains that word. So the probability of a document containing that word is exactly document frequency divided by the total number of documents. So when we observe this event, and if this event is more surprising, then we'll have more information. So if we have more information about seeing this document containing this word, that means that this word does not really occur in a lot of the document. This word is very informative. It's very content specific. It carries a lot of content, and it's not a functional word. So we have more information. So let's put the term frequency and inverse document frequency together. So we can combine the TF and IDF and together, because now both of them are the larger the better. So we can directly multiply them, and the resulting number is called TF IDF, which is essentially the process term frequency multiplying by the processed inverse document frequency. So this actually requires the term frequency to be greater or equal to 1. And because if the term frequency equals 0, then the logarithm of term frequency could go to the negative infinity. To address for this scenario, we manually decide that arbitrarily decide that the TF IDF equals 0 if the term frequency is 0. So now that we have the TF IDF number for each particular word and each particular document, so then we can vectorize each document. So for document J, there are a lot of words in the document, and also there are for all of the words in the vocabulary, we can compute the TF IDF number of that word with that particular document. So for example, word 1 and document J, and also TF IDF of word 2 and document J, all the way to TF IDF of the last word in the vocabulary with document J. So now we have, so if there are 5,000 words in the vocabulary, then we have a vector of 5,000 dimensions to describe this document. And actually, usually most of the dimensions in the TF IDF vector is 0. So then you can do some smoothing to smooth out the probability. But before that, we already have the TF IDF vectorization. And also you can do some sort of something like a principal component analysis or SVD to take the dimensions that are the most relevant. And in those cases, you can reduce the dimensions of the vectorization, and this will improve the efficiency of the IR system. So up to now, are there any questions about the TF-IDF vectorization? Yeah, question? Oh, no, it's not a question.
So, like, if the number of documents is very large, like in Google, when we are searching for web search,
yeah.
so in that case, how do we, like if we
Yeah, that's a very good question. So the question is about scaling up. So nowadays, the modern IR systems have a lot of smart ways to scale up, and mostly that includes parallelization. So they have, let's say, hundreds and thousands of computers that are running those kind of computations at the same time. And many of these computations can be done in parallel. So the actual time that are spent in computing is actually a lot faster than they appear theoretically. And additionally, the counting can be done in parallel as well. So if you are, most of the TF-IDF vectorization involves counting. And to count, you can actually place them in the bucket or shard of data. And you can designate a lot of virtual workers to count the number in each particular bucket and then take the aggregation of the counted result. So the actual number of computation is going to be a lot less than the number of documents. So yeah. And also there are a lot of smart ways to make the information retrieval systems more efficient. For example, sometimes when a new query comes in, they do not need to recompute all the TF-IDF of values of the documents. They can make some approximations, and also for example, they can also only compute the TF-IDF values for the new query, and this way this computation is a lot faster, and the vectorization of the documents can be done in the background. So when you search on the Google engine, it essentially only computes the vectorization of your query, and also the documents are stored in some ways that are very smart. So you don't need to go through all of the documents. You can actually one of the smart data structures that people use to build small scale information retrieval system is prefix tree. So when you are typing your query, it can compare your queries first a few words into some prefixes of the documents, and then it can only search for, it only needs to search for the first a few words corresponding to each document, and all of these are very fancy tricks to build the optimized information retrieval systems. And for now, for the purpose of the CSC401, we're just taking a look at the very simplified case, and we're just looking at the maximum similarity search. So on the paper, we are just going through all of the items in the knowledge base. But practically, nobody search for everything in the knowledge base, and they are doing algorithms that are a lot faster. So nowadays, the state-of-the-art information retrieval algorithm is called BM25. BM25 is still the best performing information retrieval system along many of the leaderboards. So if you want to propose some new IR algorithms, you need to compare to BM25 as a baseline. BM25 is essentially TF-IDF, but with some additional hyperparameters. So I'm not going to detail about how they set up the hyperparameters and why they set up those hyperparameters. You can check out the BM25 paper if you are interested. So for the scenario 3, we're going to take a look at the semantic doc2vec. So the idea is to use neural network embeddings instead of the engineered features. So the TF-IDF numbers are still some engineered features. So although those features are having a lot of theoretical motivations, they are still human engineered features. And as we have seen in the natural language understanding lectures, and also the beta lesson by Richard Sutton, it's better to just rely on neural networks to just do everything on its own. And when we scale them up enough and feed them with enough number of data, the neural networks are able to do some things that are a lot smarter than the human engineered features. In the information retrieval, we also need to consider the trade-offs between the trade-off between correctness and the efficiency. So sometimes the neural networks might still not able to be outperform the BM25 or TF-IDF. But the semantic doc-to-vec methods are rapidly catching up. So the goal of a semantic doc-to-vec is to train a document encoder, E. So this encoder is a neural network that takes in the text, which is usually one document or one query, and output a vector. And that vector is an embedding of a fixed dimensions. So this is an embedding vector, encoding encoder or encoder that computes the embedding vector. So we need to train the parameters in the document encoder, and one of the optimization goals can be to encourage the similar documents embeddings to be close to each other, and if the documents are far from each other, then the similarities should be small. So the distance should be distance between their embeddings should be large. So there are actually typos on the slides. So this should be large and this should be small. So if two documents are close to each other, the similarity should be large. The distance should be small, and vice versa. So the definition of the closeness varies from algorithm to algorithm. So in one recent example, which is a paper called Retrieval, they defined the positive and negative samples from according to your each of the document in the knowledge base. So they traverse through all the documents in the knowledge base, and let's say Q is the document that they are looking at. So for that Q, they find some positive samples, which they know as D+. So to get some positive samples D+, they do some paraphrasing, or they change some words, they change some sentences, and this will result in a sample that is very similar to your document that you are currently at. At the same time, you can also compute the negative samples, which are those samples that are randomly sampled from within the batches. So now you have now you are traversing through the documents in the knowledge base, and currently you are at the document Q, and you can compute the positive samples and the negative samples. You can plug them into the contrastive loss objective function, which is essentially a softmax function containing a temperature. So this is essentially the softmax of the similarity score of the embeddings computed by the encoder. And the reason why we need to apply a temperature is based on the following heuristic. So people tune the temperature of the softmax to try to change the distributions. So sometimes if you increase the temperature, you get a more even or more random distributions. And as you may remember, the more even distributions have higher entropy, and that is usually referred to the distributions that have the higher temperature. So this is why when you increase the temperature, the distribution also have higher temperature, and vice versa. If you reduce the temperature, then the distributions become sharper. So in the last hour, one student mentioned the following heuristic. So we are sampling within a batch, and we are actually not getting the distributions that exactly match the distribution outside. So we need to use some higher temperature in order to introduce some additional randomness, so that the in-batch distribution matches more the ground truth distribution. So these types of loss objective functions are called contrastive objective functions, because these types of loss contrast the positive samples and the negative samples. And the actual ways to get the positive and the negative samples actually differs from paper to paper. But in recent years, the contrastive learning scheme is quite popular in machine learning and natural language processing. So are there any questions about the methods for building information retrieval systems, like TF-IDF or semantic doc-to-vec? Okay, great. Let's go to the evaluation of the retrieval systems. So there are some commonly used metrics. For example, precision, recall, F-score, and precision at K. These kind of scores might look familiar, and these are actually almost the same thing as the evaluation scores that you use to evaluate the prediction systems. So first two of these scores are precision and recall. Precision measures the number of relevant and retrieved documents divided by the total number of retrieved documents. So among all of the retrieved documents, how many of them are relevant? So relevant documents are analogous to those documents that have the ground truth label positive in classification. And other documents are those documents that have the ground truth label 0. So the retrieved documents are those documents that have the predicted label 1, and those non-retrieved have the predicted label 0. So with this analogy in place, we can immediately figure out that the precision in machine learning is actually equals the true positive divided by positive. And true positive samples, the true positive counts the number of retrieved and relevant documents. And the positive counts the number of retrieved documents, which are the number of items that are computed and predicted positive by the machine learning predictor. So recall computes another aspect. Recall computes that among all of the relevant documents, how many of them are retrieved? So in the analogy of machine learning, this means that among all of the positive items, how many of them are correctly classified? So this is true positive divided by true. So the precision and recall has some trade-offs with each other. For example, you can build a system that returns everything in the database, and then you are guaranteed to have 100% recall, because all of the relevant documents are retrieved by you. But that system is not going to have a very high precision. So in another scenario, you can build a system that only returns the most relevant document as predicted by the similarity. So this system could have very high precision. So if you only retrieve one document, and if that document is relevant, then you have 100% of precision. But there might be 10, 100, or 1,000 items in the knowledge base that are not recalled. So the recall score is going to be low if you only retrieve one item. So the precision and recall usually have some trade-offs when you are building the information retrieval systems. And one of the popular ways to accommodate for this trade-off is to compute an F-score. F-score is the weighted harmonic mean of precision and recall. And the weight alpha is usually just taken as a fixed number, or half. And when alpha is taken to be equal to half, then the F-score becomes F1 score. F1 score is essentially 1 divided by 1 over half P plus 1 over half by 1 over 2R. So this is equivalent to 2 times P precision times recall divided by the sum of precision and recall. And this conversion is only possible if neither of precision and recall equals 0. So if one of them equals 0, then the F-score is arbitrarily set to 0. So if the true positive count is 0, then which means that there is none of the relevant documents are retrieved, then the F-score is arbitrarily set to 0. So information retrieval has a specific, has a characteristic evaluation number, which is precision at k. So the R systems do not just give one result. For example, Google search engine presents you 20 results per page. So even if the first result might be not relevant, the second and the third and the fourth result could be relevant as well. So you really need to figure out some scores that capture this kind of, accommodate for this kind of differences. And that score is the precision at k. So precision at k measures among the top k results, how many of them are relevant. So the potential problem of precision at k is that, for example, if you just take one k value, then the problem that this evaluator puts the same weight on the first item, the second item, the third item, all the way to the kth item. All of them have the same weight, although it would be really desirable that when building the Google search engine, you put the most relevant item at the top. So precision at k itself can't really accommodate for that. And another important drawback of precision at k is that if you set up k to be larger than the number of relevant items in the knowledge base, then it is impossible for precision at k to be 1. Even if you have the best system and it retrieved all of the relevant items, because there are just not enough number of knowledge of relevant items in total. So if there are less than k relevant results, then even the best system can't get precision at k equals 1. So by the end of this lecture, you should be able to describe the procedure of maximum similarity search and describe the TF-IDF vectorization, and especially describe what TF means and what IDF means and why we need to do the inverse of the document frequency. So term frequency describes the occurrences of this particular word in this document, and document frequency describes how many documents this word occurs in. And because term frequency is the larger the better and document frequency is the smaller the better, we need to do the inverse of the document frequency. And also because of some information theoretic motivation, we need to take the logarithms. And this constitutes of the TF-IDF vectorization. And we also you should be able to describe a contrastive objective function of a semantic doc2vec method. And actually, a word2vec objective function was also contrastive. So it is contrasting those words that are in the context versus those that are outside. And then you should be able to identify the evaluation metrics like precision, recall, F-score, and the trade-offs between precision and recall. And there's also the precision at k. And sometimes precision at k can't reach 100%, even for the best systems. So yeah, that concludes the lecture of today. See you Wednesday.